In this video, we'll be talking about global phase and symmetry within the spacetime algebra, specifically for bivector fields. This is the ninth kind of lesson. However, this is the eighth video. I'm waiting to make the eighth lesson until I can get one of my proofs fully worked out because there's a point where he goes from one step to another, and the step that is in between those is actually very, very long and involved. So until I get that figured out, then I'm not going to make the other video. But let's get started on this. So let's consider a global phase rotation. So a global phase rotation, and then we'll just consider on a bivector field. It happens when you say that you have some multivector in, okay, why is my thing being so weird? You have some multivector in the spacetime algebra. Then the phase rotation is mapping from M to C of M, C, and then the complex conjugate of M, where this C here is just an even field, where it's negative theta over 2, and then the pseudoscalar. So this is just an intrinsic phase here, so it's just taking the phase and rotating by it. Let's see how this phase rotation actually works when we consider it on a bivector field where its gradient is equal to 0. So we're going to be considering this right here, which was essentially Maxwell's equations in a vacuum, which is the simplest differential that you can have in the STA. Okay. And in this, say we then take a global phase rotation of this field, then that's e to the negative theta over 2 pseudoscalar gradient, then f e theta over 2 pseudoscalar, and this is going to just be, or this will anticommute with the vector that is the gradient. So you have gradient, and then inside you have e theta over 2 I f e theta over 2, and then you have, this can simplify into just the gradient of e theta I f. And then, of course, this whole thing is still equal to 0 because of this component right here, the gradient of f. So this is equal to 0. But what this demonstrates here is that the mechanics are the same when you're mapping between, so let's say the differential mechanics are don't change for the mapping of f to some phase, some global phase of this field. So what this means is that this is a constant phase that's being added to every point of the vector of the bivector x. So for example, be like this. So this right here proves that even when you map from f to a global phase of f or times f, you still get the differential is the same. which means that it wouldn't affect the ending field, or end the mechanics of it here. So the behavior under the gradient is unchanged. The behavior of this field is unchanged. So let's do another note. That is, note that e to the e theta I f is going to be equal to cosine theta, the spacetime split of the electric field, minus sine theta, and then b, then plus cosine theta, b plus sine theta e times the pseudoscalar. So this is the field. Then another note. So I'm going to have multiple notes here. So if theta is equal to negative pi over 2, then e to the theta I is just equal to e to the negative pi over 2 I, which is just equal to negative I, which is just the inverse of the pseudoscalar, which implies that this mapping f mapping to the global phase is just equal to f times the inverse pseudoscalar, which is just equal to the Hodge dual of it. Well, this, it turns out, when this theta is equal to negative pi over 2, this is just the dual. This is called the dual field. And it's called dual because it's the Hodge dual. And it's typically written as G equals Hodge dual of F, which is equal to B minus E pseudoscalar. So then the fact that the behavior of any of these phase factors doesn't change, or the fact that these phase factors don't change the behavior of the bivector field under the gradient is known as the dual symmetry in vacuum. So the fact that the gradient of f is equal to the gradient of g is equal to the gradient of any phase factor I of f, which is equal to 0, and this is for all theta in R. The fact that this is true is known as the, I'll call it this, the dual symmetry of vacuum electromagnetism. And of course, for every symmetry, there's always some conserved quantity. And in this case, the conserved quantity, or rather, this conserved quantity is more appropriately called an invariant. The invariant is the field complex conjugated with itself. So this is invariant. This is invariant under F mapping to E theta I F. So this is global phase and dual symmetry of vacuum electromagnetism.